Section 6.2, properties of radicals. The one main objective here is going to be to simplify expressions that involve radicals. Our two rules that we're going to take a look at is the following. If you have the square root of a product, you can equate that to the product of the square roots. If you have the square root of a quotient, you can equate that to the quotient of the square roots. So example A will start with the square root of 75. Right away, think you can break this up. Well, 75 could be broken up into 15 times 5. It could be broken up into 25 times 3, and 1 and 75. And we have to think to ourselves, which of those possibilities gave us a perfect square? Well, 25 and 3, because 25 is a perfect square. So we start by breaking that up, and bet that the square root of 25 is simply 5. So our final answer would be 5 radical 3. For part B, we have negative radical 8 times radical 6. Now, there's more than one way to do this. You could start by trying to break these down first or multiply them first. If we multiply them, we get negative radical 48. But 48 could be broken into 16 times 3. It's tempting to use 12 and 4 to break it down. And I'll show in a moment that you get the same answer, but it's another step. So this final answer becomes negative 4 radical 3. Let's say we had chosen to break it into 12 and 4. Reason being, 4 is a perfect square, right? And then you have the root 12 left over. But root 12 can be broken into 4 and 3 now. So this is what you would end up getting. And root 4 times root 4 is just 4. Or root 16, right? And then the root 3, carrying down the negative, obviously, the whole way. So you would get the same answer either way you did this. If you decided instead to choose either of those two methods and you chose a different method and broke this up first, this would be 4 and 2. This can't be broken into perfect squares, but you could break it into root 2 and root 3. Okay, that negative sign was over here. You could break it into root 2 and root 3, and what we'll end up noticing now is that we have the root 4 here in the front, but then there's these two root 2's right here. So when you multiply those, you end up getting, okay, that's going to be root 4 still. This becomes root 4, and then root 3, which at this point is the same line as this. Still giving us 4 root 3, with a negative out in front. My recommendation is if you can break things down initially, you should do it. So this isn't a bad root, but the problem is that the 6 can't be broken down into something with perfect squares. You have to notice that breaking it into these gives us the root 4 in the middle. Personally, this would probably be the easiest root up here. All right. Let's take a look at example C. The cube root of 25 times the cube root of 10. Well, for these problems, we have to think about the fact that now we need to look for something that could go into these that's a perfect cube, not a perfect square. So our perfect cubes, just to remind ourselves, are 1, 8, 27, 64, 125. It's kind of the furthest you're going to go, but we get right down to 216 as the last one. But what we'll notice is that neither 10 nor 25 can be broken down into perfect cubes. So what we really need to do here is to take a look at this and just multiply them to start. And we'll get the cube root of 250. Well, 250 can be broken into 125 and 2. And the cube root of 125 is clearly 5, because 5 cubed is 125. So we replace this with the number 5, giving us a final answer of 5 times the cube root of 2. And finally, part D, root 120 over root 10. Well, look at our rules. Our rules say that we can put this under one radical, so we can write it like this. And that's just simply going to be a 12 left behind there. And then 12 is really root 4 times root 3, so this is 2 radical 3. All right, example 2 is the same thing we just did, but now we're looking at variables. So we're looking for the square root in the first one of 3ab squared. So again, we need to separate it, break it into a perfect square and then a non-perfect square. Well, b squared is clearly a perfect square. 3a is not a perfect square. Now, when we take the square root of b squared, we have to remember that we're looking at the principal square root. Whenever there's no sign in front of here, when there's no sign here, we're looking at the principal square root. Well, remember that when you take a square root of a number, we always think about that negative or positive, but because we're looking for the principal square root, this becomes absolute value of b times the square root of 3a. Part B says the square root of 49y to the fifth. What we're going to notice here is that 49 is clearly a perfect square, but then y to the fifth we have to think about. So here's what I would do. I would definitely write the 49 here. Well, if I have a y squared, that's a perfect squared. I could have another y squared as a perfect squared, leaving me behind just that simple y. Because technically speaking, right, y squared, and y, that's y to the fifth. So these are both perfect squares. So what we end up getting here is just 7, absolute value of y, radical y. But what you'll notice is that you have the absolute value of y twice. So that's a product of those. So it would end up becoming this. But if you're squaring a number, you always get a positive answer anyway. So this is the square root, or this is the principal square without the absolute value. So you can just write it like this now. So you could drop the absolute value because you're squaring it anyway. So it's got to be positive. What you might pick up on at this point now is the fact that since we had y to the fifth, we could have just broken this up and made this y to the fourth instead. Right? You could have made this y to the fourth times this y over here. Well, this is just y to the fifth. And then y to the fourth, the square root of y to the fourth is just y squared. So you could then just jump right to that answer. So there's no need to break it up into y squared multiple times. Just think of this as y to the fourth. And remember that your index here is really a 2. So the rule that we came up with last lesson is that you could take this 4 divided by this 2, and we'll get the exponent that remains here. Part C says the cube root of w to the fourth over y to the third. So what we'll notice here is we'll have to remember, okay, we can break up a fraction that's inside of a radical as follows. And now what we'll get is that the cube root of y cubed, that's just y. Right? The cube root of y cubed. And you can remember, just divide the exponent by the index. Well, up here I can't do that. So I have to break this into the cube root of w cubed times the cube root of w. Because in the end, isn't w cubed times w just w to the fourth? Yeah. So now this cube root of w cubed just becomes a w times the cube root of w all over y. Part D says square root of 9w squared plus 9u squared. Now it's really tempting here to make the common mistake and take the square root of each part. But you have to remember, if you have a sum under a radical, you cannot take the individual square roots of each term. You have to have factors. So start by factoring out a 9. And now we can break this radical up. Break it into radical 9 times radical w squared plus u squared. Well, this still cannot be simplified because there's a plus sign. So please don't make this w and don't make this u. You can't simplify it because of the plus sign. You need to have a factor in here, or they need to be factors so you could separate them like we separated this 9. This just becomes 3, giving us a final answer of 3 radical w squared plus u squared. Finally, example E says the square root of x squared plus 12x plus 36. Well, again, we need to factor things. Well, that factors into x plus 6, which is really, if we remember, just the quantity x plus 6 squared. Which in the end, when taken the square root of, becomes absolute value of x plus 6. Now we're going to take a look at rationalizing a denominator, and we're going to see that this next process, although it's less important since we've introduced calculators into the world, it's still a good technique that's used in calculus class that helps simplify some complex expressions. And the main idea here is to create a perfect square or a perfect cube or whatever the perfect power we're looking for is based on the index in the denominator's radicand. Okay, whatever is needed here, in order to simplify the expression to get rid of the radical in the denominator. So let's take a look at how to do that. If we have the square root of 7 over 3, Well, again, before calculators were invented, you would use a square root table, and it's a lot easier to take a square root of only the numerator and then divide it by an integer value. But if you did this without a calculator and you had the estimates, and you had the square root of 7 with a bunch of decimals and the square root of 3 with a bunch of decimals, it's very difficult to divide those two quantities without a calculator. So what they did a long time ago was they made the numerator a radical and somehow made the denominator transform into an integer. Let's take a look at what I mean here. Well, if I take a look and I say, well, this is really just root 7 over root 3, and if I want to create a perfect square in the denominator, well, a perfect square in the denominator to make would be just to multiply by this by root 3 over root 3, because this is really 1. And now if I multiply these two, I get root 9, and root 9 is just 3. So this ends up becoming 3 in the bottom, and the numerator becomes root 21. So again, before calculators were around, it would have been a lot easier to just look up the value of root 21 and then divide it by 3. Instead of finding the value of root 7 and then the value of root 3 and dividing those decimals, that'd be a lot more work. How about part B? Part B, we have root 3 over a. So I'm going to write it as root 3 over root a. And I'll multiply by root a over root a, using part A as my template here. Well, this creates radical 3a over radical a squared. Well, that's just going to be radical a squared. Now here, this actually simplifies to radical 3a over just a. We don't need the absolute value here simply because we know already that a is positive. A had to be positive. If a were negative, then this would be non-real. Okay, and we're looking at only real numbers here. So we can just leave this as a. Part C says the fifth root of c over the fifth root of c squared. Well, if I want to get a perfect fifth here, because I have the fifth root, I need to have 3 more c's in the bottom. But again, it's under the fifth root. So I have to put that up top if I'm going to put it in the bottom. So that's my multiplying factor. Well, this becomes the fifth root of c to the fourth all over the fifth root of c to the fifth. Well, the fifth root of c to the fifth is simply just c. So we can just put a c in this place right here, and we're done with this one as well. Part D says the cube root of 3x to the 7th, y to the 2nd, all over 48x to the 3rd, y to the 4th. Well, this kind of a problem, it helps to start by simplifying. Well, 3 over 48 is 1 over 16. So in the numerator, I leave behind a 1, which doesn't matter. And then it's 16. X to the 7th and x to the 3rd, 3 of these cancel with 3 of these, leaving behind 4 x's up top. And then 2 of these cancel behind with 2 of these, leaving 2 y's down below. So this is what we've got now. But we're looking for perfect cubes now. Perfect cubes. So we could rewrite this as, again, the cube root of x to the 4th over the cube root of 16y to the 2nd. If I want perfect cubes, I need to get something that has a cube in it. So I need at least y to the 3rd in the bottom. So I'm definitely going to multiply by something with a y in it to get y to the 3rd. And then I want 16 to become a perfect cube. Well, the perfect cubes again are 1, 8, 27, 64, 125. Well, let's stop at 64 because 16 times 4 gives us 64. So we multiply top and bottom by the same thing, yielding in the top the cube root of 4x to the 4th y all over the cube root of 64y to the 3rd. Well, the bottom is simple. That just becomes the cube root of 64. Well, that's 4. The cube root of y cubed is just y. Now in the numerator, I can break this up into x to the 3rd and x. So I'm going to write it like this. Okay, because again, the top, x to the 3rd here, and this x become x to the 4th. And this simplifies to just become x. So our final answer here is going to be x from this part here times the cube root of 4xy all over 4y.